Hello. In the previous video, we had seen how a attacker, essentially an unauthorized user of the system, could cause his own code to execute in the system by exploiting what was known as a buffer overflow bug. So, we had seen, at least we had created such a buffer overflow bug and shown how the attacker could create his exploit code and run that exploit code, which created a shell in the system. So, this particular example was an application based example in the user space, but very similar kind of exploits can be written in the operating system. So, what we will be seeing in this video are techniques of how this buffer overflow vulnerability is overcome, and also how the attack has progressed over the years and evolved over the years to make more powerful attacks in order to overcome these protections. The first and the most obvious way to prevent the buffer overflow attack which occurs in the stack is by making the stack pages non-executable. What we've seen is that the attacker would force the CPU to execute an exploit code which is also present in the stack. So, for instance, over here this buffer which is defined on the stack also contained the exploit code, and the string copy was executed in such a way that after string copy completed its execution, it would cause the exploit code, that is the shell code which is present on the stack, to be executed. So, one obvious way to prevent this attack is to make the stack pages non-executable. So, and this is what is done in systems that are used these days. So, if you would actually run this particular program on your Intel systems, and instead of getting the exploit code to execute, you would get a segmentation fault. This would be caused because the program is trying to execute some instructions onto the stack. In Intel machines, an annex bit is present in the page tables to mark the stack as non-executable. While this works for most of the programs, that is, in most programs it is a added benefit, but the problem is some programs, even though they may not be malicious, require to execute from the stack. So, these programs need to execute from the stack in order to function properly. Therefore, setting the annex bit is not always very beneficial for all programs. So, the next thing we are going to ask ourselves is that if we make the stack as non-executable, will it completely prevent buffer overflow attacks? And in fact, it does not. Over the years, buffer overflow attacks have evolved to something known as the return to Libc attacks, which could be used even on systems which have a non-executable stack. So, let us see in very brief how a return to Libc attack works. So, essentially what we have done when we try to overflow the buffer in the stack is that we had the exploit code present onto the stack, and we had replaced the valid return address with the address of the buffer. Now, this did not work for us in modern day systems because the stack was set to non-executable. So, let us look at how return to Libc works in spite of having the non-executable stack, that is, in spite of having the annex bit set. So, what the return to Libc does is that instead of forcing the return address to branch to a location within the stack, it forces the return address to go to some other location containing some other function. Let us say this function is F1. So, what is filled onto the stack through a buffer overflow is a pointer to F1. Therefore, when the function completes executing, the return address taken from here is a pointer to F1, and therefore, the CPU is forced to execute this function F1. Now, the next question is, what is this function F1? So, one thing is certain, that this function cannot be the attacker's own exploit code. So, it has to be some valid function which is already present in the code segment and which has the permission to execute. So, what would this function F1 be? That is point number 1. And point number 2 is, how will an attacker use a normal function which is present in the program to do something malicious, such as to run an exploit code. There are various ways in which the function F1 can be implemented, but what we will see today is the function F1 implemented using this particular function called system. Now, system is a function which is present in the library called Libc, and what it does is that it takes a character pointer to a string which would take an executable. So, the string which is passed to system takes an executable name, and when executed it would essentially execute this particular program. So, in this particular example, what system would do is that it would execute the bash shell, thereby creating a bash shell. Now, Libc is a library which is used by most programs. So, even a normal hello world program that you write would quite likely use the Libc library. So, what this means is that in your process's address space there is the function system. So, what the attacker would need to do now is to just identify in your process's address space where the system function resides. Next, he needs to somehow pass an argument to this in order to run a program. So, suppose let us say, if we are continuing the example what we seen in the previous video, where the attacker creates an exploit which executes a shell. So, in this case also, if the attacker wants to execute the same shell, then in addition to finding the system's function's address in the memory space, the attacker would somehow needs to pass this particular string /bin/sh as a parameter to the system. So, this means that the attacker would need to find an address that points to the string /bin/sh. So, what is typically done is have a stack frame something like this, where the return address, or rather the valid return address, is replaced by F1 pointer, which is a pointer to the system function which is present in Libc. And if your program uses the dynamically linked library Libc, then such an address will be valid. Second, what the attacker needs to do is to pass an argument to the system function which essentially has an executable name. So, essentially somewhere in your address space, the attacker needs to find this particular string being present, that is /bin/bash or /bin/sh, and fill in the stack with a pointer to this particular string. So, essentially it requires two things. One is the return address in the stack to be modified with the address of the system call which is present in Libc, and also the parameter passed to Libc should be present onto the stack on the stack. So, in this case it is a shell pointer which points to this particular string /bin/bash. So, once this is done, when the function returns, instead of returning to the valid address, it is going to cause the CPU to execute this particular system. Now, during this process also the pointer to this particular shell /bin/bash would be considered in the system call, and it would result in a shell being formed. So, from this shell the attacker could then spawn various other things and run his own programs. So, in this way the return to libc attack works in spite of having a stack which is non-executable. So, note that we are not executing any of these instructions, we are just reading and writing to the stack, while the real execution occurs in the code segment itself by the function system. Now, the limitation of the return to libc is that it is extremely difficult to execute some arbitrary code. So, we had seen one example of how the attacker could execute a shell, but the amount that an attacker could do with a return to libc type of attack is very limited, and therefore the attacks over the period of time have evolved to some things more stronger, and more recently there is something known as the return oriented programming attacks. So, this is one of the most powerful attacks that are known which utilize buffer overflows. So, this is also applicable for systems which have non-executable stack. The return oriented program, or also for short known as the ROP attack, was discovered by Shacham in the Stanford University, and it allows any arbitrary computation or any arbitrary code to be injected into the program in spite of having a non-executable stack. So, let us see with a very small example how this thing works. So, let us say that the code that the attacker wants to execute is given by these set of assembly lines. So, essentially if the attacker manages to execute these assembly code, then his job is done. He will be able to run whatever exploit he wants. Now, what the ROP attack does is use something known as the gadget. Now, gadgets essentially mean splitting this particular code or the payload as it is called into small components which are known as gadgets. So, it has been shown that a variety of different payloads could be executed just by using gadgets, and therefore, we could have a variety of different exploit codes that have been used by the attacker. So, let us see what a gadget is. So, essentially a gadget is some useful instruction, and when I say useful instruction over here, it means that it is one of these instructions in the payload that it needs to be executed as part of the exploit, followed by a RET, a return. So, RET, as you know, in the Intel instruction set, it means the return from the particular function. So, this very simple thing is what is a gadget. So, now what the attacker needs to do is, corresponding to the payload that he wants to execute, he needs to scan the entire binary code of the executable in order to find such useful gadgets. So, for instance, if we take this particular payload, the attacker may find that somewhere in the program's binary, that is among all the instructions that are present, there is this particular gadget present which does almost the same thing what is required. That is, this particular instruction in the payload is move ESI, 0x8 ESI, and this exact same thing is present over here. Similarly, what the attacker would do is he would scan the other parts of the program binary in order to find more such gadgets. So, the second line in the payload is present in the gadget 2, the third line is present here, and so on. So, he essentially what he would do is force this payload to execute by using gadgets. So, what he is going to overflow the stack with is a chain of gadgets. So, essentially the stack is going to contain G1, then G2, G3 and G4. So, these gadgets are, or the addresses to these gadgets are organized in such a way that when the first valid return address is met, instead of finding the valid return address, the address of gadget 1 is found, and as a result this instruction corresponding to gadget 1 is executed, and then there is a return, and the stack is arranged in such a way that gadget 2 will then execute, then gadget 3, gadget 4 and so on. So, in total, although the instructions are not in contiguous locations, what the attacker has managed to do is he has managed to execute all these instructions. So, in this way he is able to execute his payload, and it has been shown that a large set of such gadgets are feasible in programs. So, other precautions for buffer overflows is to use a programming language such as Java, which automatically check array bounds. So, this will ensure that no array is accessed out of its limits. Another way is to use more secure libraries. For example, the C11 specification annexure K specifies these securer libraries to be used. So, for example, the get s underscore s, string copy underscore s, string n copy underscore s. So, all these have the same functionality as the standard functions that we use, but these functions are secure and would prevent buffer overflows. Another popular use to prevent buffer overflows is by the use of canaries. So, a canary is a known pseudo random value which is placed onto the stack in order to detect buffer overflows. What is done is that at the start of the function, a canary is inserted onto the stack, push some canary value onto the stack as shown over here. So, in addition to the parameters, the return address, the frame pointer, we have now a canary also, and just before returning or leaving the function, the canary is checked to find out whether it is modified. Now, if a buffer overflow occurred, then as we know, the buffer overflow would modify the addresses in the stack, and as a result the canary value would be modified, and therefore we would be able to detect a change in the canary value if a buffer overflow occurred, and therefore we will be able to perhaps stop the program. So, in these days, in recent versions of the GCC compiler, such canaries are implemented by default. So, this being said, the entire use of canary is evaded if the canary value is known. That is, if the attacker manages to know what the canary value is used, then he could just change or set this value of canary in such a way that this canary is not changed at all, and therefore its use is limited. Another way to prevent this particular attack is something known as the address space randomization, or ASLR. In this particular countermeasure technique, it uses the fact that the attackers need to know specific locations in the code. In the return to Libc attack, for instance, the attacker needed to know where the function f1, or in our example where the function system was located in the program space. Now, if we had ASLR enabled, then the layout of the address space is randomized. Therefore, the attacker would find it difficult to determine where exactly the function is present that needs to be exploited. In other words, the attacker would find it difficult to find out where the function system is present in the address space. Thus, it would make the attack much more difficult. Thank you.